Hi, I'm Sanjith.
And I'm Annie, and we built FPGAceTime, high-speed video and audio transmission between these two FPGAs. Both have cameras and microphones connected to them and will display the videos on the screen.
Yeah, so you can see we've got one monitor hooked up to each FPGA showing what their FPGAceTime view looks like. And you can see this near real-time stream of 320 by 180p 16-bit RGB video at approximately 18 frames per second with constant audio feedback as well through the microphone. And just like real FaceTime, we have all the features like a received view. So this is like Annie's view, and you can see her selfie cam in the bottom right. This is my view, you can see my selfie cam in the bottom right. And just like real FaceTime, you can even zoom in on the selfie cam. Hi, Annie.
Hi.
Yeah. And now we'll demo the audio.
So we also have continuous audio working, where if I speak into my microphone, Sanjith will be able to hear through his earbuds exactly what I'm saying in real time. We'll demo this where I can whisper a little statement so that hopefully the camera doesn't pick it up where I'm whispering it, but you can pick it up on the headphone side.
Not sure if the camera picks it up, but yeah, that's FPGAceTime, and now we'll dive into how it works.
Here's kind of what it looks like at a high level. It's pretty complicated, but you can see this is one FPGA, this is another FPGA, but really they have the exact same circuit. How it works is we have 8 PMOD pins available after we have the camera plugged in. To ensure signal integrity, we decided to use differential signaling, which is kind of what these O-buff and I-buff DS modules are. What this means is we actually have the number of pins we have, and we only have 8 pins left since we need a positive and negative end for each. This means we'll only have a transmitting clock, transmitting data bit, receiving clock, and receiving data bit. How it works is when we receive the camera data, we'll do some downsampling and anti-aliasing, which gives us 320 by 180 in the end. We'll construct some packets, which we'll talk about later. Then we'll serialize these to send them one bit at a time to the other FPGA. Then when we receive it, for example, over here or over here from that one, we'll have to construct the packets again into these 18-bit packets, which will then be able to display either on the monitor or through audio. We arrived at using 20 megahertz as our as our transmission clock because we wanted to ensure both signal integrity while also having a consistent frames per second.
So our two FPGAs are sending these 18-bit packets between each other. And the format that we decided on was to have a 2-bit header and a 16-bit payload. The 2-bit header signifies the type of packet. So it could be either audio or pixel data, signifying a frame start, or a sync packet, which I'll explain in a second. And the payload contains the actual either pixel or audio data. However, an interesting problem we ran into, given our pin limitations having only a bit and a clock signal, was that we didn't actually have any way of having the deserializing end aligned to when a packet started and when a packet ended. And this is an important problem, so the way that we decided to solve it was by implementing a self-correcting bit alignment protocol. And the way that this works is the transmission end at regular intervals sends a fixed low autocorrelation sync word. And on the receiving end, regardless of alignment state, if a sliding window finds that in like the last 18 bits that were transmitted, we saw the sync word, it'll force realignment, which allows our system to be resilient to any sort of clock slippage, allowing us to bump up our transmission speed to 20 megahertz.